Okay, so moving on to where the rubber hits the road, why we dealt with the series in the past few sections is because we want to talk about power series and what these things are. So, real quick, brief explanation of what a power series is. What a power series is a series with some variable in it, not like n, but like x, like our typical variables, that's being raised to some power. That's why we call it a power series, because we have a variable raised to some power. Let me write that down and explain what they would look like. So a power series, it's simply a series with a variable x that is being raised to some power. And that power is based on n. Now, what we're going to talk about in this class are two types of power series. We're going to talk about power series centered at 0, and we're going to talk about power series centered at some constant c. So there's two types we talk about. Other than the fact that they're centered at different places, there's really not any difference between them. So there's two types of power series. Power series number 1. Power series number 1 looks like this. This is going to look very interesting to you because you've never seen it before. It's a series. We start them at 0. So the first term starts at n equals 0, typically. And what it's going to look like is, well, that would be just a normal series, wouldn't it? Just a sub n. Something like, I don't know, n squared over n cubed plus 1. That's a type of a sub n. Or whatever we have. We've had many of them. ln over square root of n, whatever. We had a lot of different types of sequences from where we get our series. Now for a power series, the difference between what we've done before and what we're doing now is instead of just having this, we also have a variable raised to some power. That's what's giving this idea of a power series. It's now has a variable in it. Does that make it harder or easier? Just different. It's going to use a lot of the same concepts that you already know. We're still going to be doing things like the ratio test and absolute convergence and all sorts of that stuff. We had to have that, and you're going to see why as we go through this section. Okay, so when we get down to checking for endpoints, when we get down to radius of convergence, when we get down to finding out whether these are convergent or not, we're using the same tests. Okay, it's all the same stuff. So we had to have all that so that we could accomplish this section. So let's talk about what this would look like. Just the first couple terms, how it's going to look. Where do we start these power series? So if I plugged in 0, well, I don't know what this is explicitly, but I know it's going to be a sub 0. True?
Yeah.
And it'll be x to the 0. What's x to the 0? 1. So our first term is simply going to be a sub 0. Are you with me on that one?
Yeah.
And we're going to go, okay, plus. It's not alternating typically unless we have something in our a sub n that makes it alternate. Plus, I would plug in 1, and I would get x to the... Good. And then I would plug in 2, and I would get x to the second. I'd plug in 3, and I'd get x to the third, and so on and so forth, forever and ever and ever and ever, because this thing stops at infinity. You guys okay with that so far?
Yeah.
Now just a little heads up, I want you to think about functions. Do functions ever stop? No, functions go into it. So right now what we're doing here is we're actually defining a function, which is interesting. We'll talk about that in a minute. So number 2. The other type of power series you can have is one that's centered... Oh, you know what? I forgot to tell you a little something. I mentioned it, but I want to write it down for you to make sure you have it. What this is a power series in the variable x, which is centered at the origin. The origin would be our 0. I said centered at 0, centered at the origin. You can use them interchangeably. This is centered at 0 or centered at the origin. So this is a power series in x, which is our variable. This means it's a power series based on the variable x, which is centered at the origin or 0. Why is it centered at 0 or centered at the origin? Why is it centered there? I want you to look at the x. Is anything being added or subtracted from the x? So 0 is being added or subtracted from the x. Nothing's being added or subtracted. Therefore, it's centered at the origin or centered at 0. Quick hit note if you're okay with that one. Compare it to this. Suppose I had a series, started at 0, never ending, a sub n, x minus c to the n. Of course, the first few terms are going to look really similar to this. Let's check that out, and then we'll consider the differences between our series themselves. If I plugged in 0, I'd still get a sub 0. I'd still get x minus c, but this is going to be raised to the 0 power. What's anything raised to the 0 power? 1. So it starts out exactly the same. Do you see why? Mm-hmm. Plus, I'd still have a sub 1, but this time instead of having x to the first, I'm going to have x minus c to the first. And instead of having a sub 2 times x to the second, I'm going to have x minus c to the second. Other than that, there's not any change to it. It's just where this thing is centered. So that little c that says x minus c, that c is what your center is. So if I have minus 3, we're centered at 3. If I have plus 2, we're centered at negative 2. Did you catch that? Are you sure? Because it's minus c, so minus negative would make that plus for us. So anyway, we have a power series in x still, but this is centered at c. Where c is, it's a constant. Now, of course, I'm going to give you some examples in a little while, and we'll talk much more about this as we go through. But for right now, we're not going to work with these things. I just want to give you examples of how they look. Would you guys like a couple examples of how these things look real quick? Please. Okay, so here's an example. Just for a few terms, we'll see what these things are doing. And of course, we'll talk a lot about them as we move forward. You know, the first thing I want to know if you can tell that this is going to be a power series just by looking at it. Can you tell it's going to be a power series just by looking at it?
Yes.
What's it got there that none of our series before is? Yeah, I mean, it's a variable being raised to a power. That's a power series. Now, quick question. Do you think this is going to be centered at 0 or centered at some other number? Centered at the origin or not? What do you think? Does it look like number 1 or number 2? Looks definitely like number 1. Because we have nothing being added or subtracted to our x itself. If it's not centered at the origin, it's going to be x minus or x plus something. Not sure if you understand that. Okay. Also, can you pick out my a sub n from here? Can you pick out my a sub n? What is it? Just cover that up. And that's a sub n. That's it. So this is the sequence, right? And then after that we're getting our series from. And then after every term, we're just tacking on an x. X to the 0, x to the first, x to the second, x. That's what's giving us our power series. So really, if we wanted to do this, we could write out just the sequence here and put x to the 0, x to the first, x to the second, x to the third after every single one of those terms, and we'd have the appropriate series. Now, of course, we're going to do this all at one time, but let's try it just for the first few terms. Where do I start again?
0.
Let's plug in 0. What's negative 1 to the 0? 1. So we're going to have 1. What's x to the 0?
1.
And what's 0 factorial? 1. 0 factorial is defined to be 1. If you didn't know that, it's 1. So our first term here is 1. You okay with that so far? Next term, let's plug in 1. If we plug in 1, what's negative 1 to the 1?
-1.
So I know I'm going to be subtracting. Hey, what type of a power series is this?
Alternating.
It's alternating. Yeah, that's right. So how about plug in 1 here? We get x to the... Over? Over what? Over 1. Over 1 factorial. You could put the 1 factorial here if you just want to see the pattern. Okay, so right now we just have x, but if you put 1 factorial, you're going to see the pattern in just a minute. Next one, is it going to be plus or minus, everybody?
Plus.
Sure. And what we'll get is
1.
x to the second over...
2 factorial.
Good. Minus x to the third over 3 factorial plus. And do you see the pattern? It's easy to see the pattern once you get the first few terms. That right there is the first few terms of our power series. Let me give you the next one. I'll make a couple statements about this. I do want you to understand that this thing is centered at the origin there, though. Have I made that very clear for you?
Yes.
So it's a power series, no problem, because it's got x to a variable. You notice how the variable here is 1, 2, 3, blah, 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 blah. It's going to continue. We have it centered at 0 because nothing's being added or subtracted from our x. Now compare it to this next one. What's that going to do for us? Okay. Okay, it might look a little nasty, but don't worry about that right now. We're just going to kind of talk about this one for a second. First thing you notice, what type of a series is this? This is a power series.
Yes.
What tells you it's a power series?
Variable to
It's a
it.
variable. It's been raised to a power. Now, let's see. Is this more like the number 1 or more like the number 2?
Number 2.
So is this centered at the origin?
No.
Where is it centered?
Power 4.
Very good. Do you understand why it's not centered at negative power 4?
X minus.
That's right. It's x minus the center. Just like finding a root, like if you did x minus 2, the root of a polynomial, x minus 2 means your x-intercept is at 2. So that positive 2. You can think about it like always a changing sign. Well, it's not really. It's defined to be x minus your center, so the center is pi over 2. If I had x, oh my god, sorry, I said pi over 2, I meant pi over 4. If I had x plus pi over 4, the center would be at negative pi over 4. Very good. Yeah, exactly right. So, let's figure out a few terms here. What's the first thing we plug in, everybody?
0.
So if we plug in 0, we're going to get, let's see here.
1.
Here's 1. Plug in 0 here. Oh, wait. So am I going to start with,
Nope.
oh, that's going to be different than we had before. So this actually does something here. So don't just automatically assume we start at 1 all the time. That doesn't work. So this does give us 1. This gives us, well, 2 times 0 is 0, plus 1 is 1. So we're going to start with x minus pi over 4.
Over 1. No.
If I plug in 0 here, I get 1 factorial, which is just 1. You guys okay with that so far?
Yep.
Next term, is it going to be positive or negative, plus or minus? Yeah, this is an alternating series because that thing is alternating. So we're going to get minus. I'm still going to get, notice what happens here. And what doesn't happen here, actually. Are there any n's in here at all? So is this thing ever going to change?
No.
No, it's not changing. So you're going to be writing things like x or x minus pi over 4 over and over and over again. The thing that changes is the power. It's a power series. The power is changing of our variable. And this denominator. So I still have x minus pi over 4, but my power is going to change and my denominator is going to change. What's my power going to be? Remember that I plugged in 0 first. I'm going to plug in 1 now. What is it? So this is to the third over, and notice how this is the same as this. So if this is 3, this is 3 factorial. If this is 5, this is 5 factorial.
3 factorial.
Plus we have x minus pi over 4 to the 5th over 5 factorial. What it's giving us is odd numbers. The next one would be 7 over 7 factorial, 9 over 9 factorial. Does that make sense to you? That's our power series centered at pi over 4. Now, we're going to talk about the theory, kind of some notes behind this. First thing, do you notice that when I'm doing this, when we're doing this, we're actually getting a function out of it? Do you see that? We get a function based on x, so a function of x. These power series are all going to create functions of x. So, if these things create a function of x, then what we can do all the time with our power series, do you understand that what I'm talking about, a function of x? Yes, no? If I actually do the series, there's no more n's. the n does 0, 1, 2, 3, 4, 5 to infinity, what I get is a series of terms, all of which have variables in them, and that variable is always x. Does that make sense? It's a function of x. So what that means is that I can define a function of x to be equal to my power series. By the way, I'm wondering if you understand why I'm using this form of our power series rather than this one. Do you understand that this form is like the general form of this? If I have c equals 0, then it gives me this one. So therefore, I can always use this and be correct as far as my general power series. Quick head now if you're okay with that one. Okay, so does that make sense to you? If this thing is a function of x, we already said it was, because what happens is I'm going to get, a sub n is going to be a number, a constant number for every individual term, and when I put 0 or 1 or 2 or 3 or 4 or 5 or whatever into my n, that's going to be a constant. This, of course, is going to be a variable, that's going to be a constant. So I'm going to get a function in terms of whatever my variable here is. It's going to be a function in terms of x. Now, this is what's going to be interesting. Please listen carefully. If I have a function equal to my series. Oops. When I plug in some x, I'm going to get a series of terms, correct? That series is either going to converge or it's not going to converge. Does that make sense to you? So I'm going to have a series, I'll have x's in it. You say, hey, give me an x. Okay, whatever you give me, I'm going to plug in my x. Either this series will converge or this series will not converge. Does that make sense? If the series converges, we would get a sum out of it. Does that make sense? If the series does not converge, of course, we wouldn't be able to find the sum. So if the series converges, we get a sum. That sum is the output of my function. The input of my function is, of course, my x. But I only will get a valid output if my input makes my series convergent. Let me go through that one more time because this is kind of the theoretical, like, wait a minute, does that make sense to me? Let me say it again. Okay, here's what's happening. When I plug a number in, it's going to create a series. So plug a number in for x, not n. N's already 0 to infinity. I'm plugging a number in for x, here and here and here and here and here, whatever. I'm going to get a series that either converges or diverges. Does that make sense to you? If it converges, I get a sum. That sum is the output of my function. If it does not converge, diverges, then I don't have a valid sum. Okay, it'd be like infinity or it would be undefined. We can't do that. So what we're saying here is this function is defined with a domain. Remember that domain's all the things we plug in? With a domain of all x's such that the series converges. This is a function with a domain of all x's such that the series converges. If the series does not converge, then I don't have an output for my function. Does that make sense? Do you need me to explain that one? I tried to explain it 3 different ways, but they all end up sounding kind of the same because it's the same idea all three different ways. It's the same thing. Are there any questions on this idea? I know we haven't done any examples, but I want to make sure this is clear before we go absolutely any further to make sure that you get it. Do you get it that this thing can be defined as a function of x because x is a variable? Do you understand that series either converge or diverge? Okay. Do you understand that for certain values of x, this series will converge, and for certain values of x, this series will diverge some of the times. So sometimes you plug in anything, it's going to converge. Sometimes you plug in anything, it's going to diverge. But a lot of the times we have some x's that's going to make the series converge, and some x's that's going to make the series diverge. Do you get that? Do you understand that if the series diverges, I can't really represent this very well with a function? Because I'm not going to have a sum. The sum is my output. I sound very southern, my output. The sum is my output. Therefore, when you put in an X, that gives me
No,
a sum.
when y'all put it
Then
in.
I get, when y'all put in an X, I should say y'all. When I was 13, my parents took me on a trip around the United States, and we spent a long time in the South. And so I actually did pick up an accent from down there in Louisiana and Texas and all those places. So by the time I got to Boston, I sounded all messed up. 13, you know, that age, you're picking up a lot of language. So anyway. Anyhow, so if this thing is a function of x, and I plug in certain numbers of x, some will make it convergent, some will make the series divergent. Those values of x which make this series convergent mean that I get a sum for those values of x. If a series is convergent, I get a sum. So for the values of x which make this thing convergent, I get an output of my function. Therefore, we have a function with a domain of all x's that make my series convergent. The x's that make the series divergent, we don't care about because we can't define the function there. Show of hands if that made sense. Okay, you understand a power series then. That is what a power series is. Now, let me give you a couple examples on how we actually do this and what we can do with it. Not any hardcore examples yet. We're still kind of on the note-taking part of this. So, we got the power series idea. Power series idea does make a function so that our domain is all the x's that make the series converge. That's it. Now, let's look at what we can do with it. Let's start with the most basic power series I can think of. It's just this. The series of n equals 1 to infinity, from 0 to infinity of x to the n. Firstly, is it a power series?
Yes.
Okay. What's my a sub n?
1.
It's 1. Yeah, that's a very simple power series, but it's still a power series. Let's look at, some of you guys zone out. Don't zone out on me here. Let's look at the first few terms just to get an idea about what this is. What's the first term here?
1.
Next term? Next term?
X squared.
Good. And then it
X
continues forever and ever and ever. Here's what's kind of interesting. These power series are going to represent series a lot of the times that you've seen before or that you can work with in the same manner you work with the other series. For instance, this right here might look weird to you. This is a geometric series. That's all it is. It's just a geometric series, and I'll show you why. This is simply a geometric series. Do you see it yet? No? Let me put this on the board. Do you understand that a geometric series is a times r to the n?
Yes.
That's a geometric series. Well, if that's a geometric series, by the way, sorry, when does this thing, do you remember when it converges?
Absolute value of R.
It's all based on the r.
When r is less than 1.
Above absolute power.
I see the value of R.
It's greater.
Less than 1.
Greater or equal to?
P series greater than 1.
Okay. Make sure it's on your note card.
No card. No card right now. Yeah, by the way, that R, I don't know if I ever told you this, that R is called the common ratio. Did I ever tell you that?
No.
It's called the common ratio.
Like 20 sections later.
Whatever. So, a geometric series converges when the common ratio R is, in absolute terms of absolute value, is less than 1. That's what this thing is. Now, I want you to consider this for a second. So, the series x to the n has a common ratio of x.
Oh.
Look up here. Does this fit this format?
Yes.
What's our A? No,
One.
the A is
1.
1. A would equal 1. What's taking the place of our What's taking place of our r?
X.
The x. That's why I said it has a common ratio of x. That is the r in this case. So what's really interesting is that this thing is really a geometric series. Now, the question is, when do geometric series converge?
When ours.
When the R is less than
Absolute
1.
Okay,
value.
so I don't want to lose you here. Do you understand the idea? I'm trying to make this look like a geometric series.
Yeah.
It is a geometric series. It's just that A is 1, the R is X in this case. That's geometric. Now, if geometric series converge when the absolute value of R is less than 1, then this series converges when the absolute value of X is
0. Less than 1.
not 0.
Less than 1.
Less than 1.
Less than 1. That's the idea of the common ratio. The common ratio, well, okay, it says converges if the common ratio is less than 1. This has a common ratio of x. It will converge if x is less than 1 in terms of absolute value. Or if you want to think about it this way, when negative 1 is less than x, which is less than 1.
So is this diversion?
It's convergent.
Let's talk about it one more time just to make sure that you are with me on this thing. First things first, are you starting to see that this is geometric?
Yes.
It is this. It just happens that r is no longer a constant, it happens to be a variable. Now, what we know about geometric series is that geometric series converge every time this number is between -1 and 1. Therefore, I don't give a heck what, that's not even, it's a thing now. I don't give a crap what this is,
In India.
what this is, as long as this number is between -1 and 1, non-inclusive. Does that make sense to you? That's what this says. I don't care what this number is, as long as it's between -1 and 1, non-inclusive. This will converge. This would, if I give you -1/2, is that going to converge? How about -1/3, -1/4, -1/5, -1/6, and then forever until you get to 0? How about 0? How about 1/2? How about 1/3? How about 1/4? All the way to, yeah, it's going to converge for everything, as long as this is between, as long as this is between, because this is that. It is a geometric series. Does that make sense to you?
Yeah.
You sure? So our domain is right here. Remember that, the whole thing? Hey, this thing, that defines a function of x, doesn't it? Are you catching this picture? This defines a function of x. When will this function of x converge? It will converge when x is between -1 and 1. That's what we're saying here. This is a function on a very specific domain. Is it a function defined everywhere, folks? Everywhere? No. It's defined for a very specific set of x's. What's the set of x's that this is defined to be? So that's our domain. That's it. Now, here's what's also very cool. Do you know how to find the sum of
Yes.
geometric series?
A over 1 minus R.
So in our case here, the sum is a over 1 minus r. A over 1 minus r. Check this out. So if f of x, this is kind of how we'd write it mathematically, okay? I said a lot of words here. You didn't say very much. Forget you guys, but I said a lot of words, all right? Here's what this says. This says I have a function. This is a function of x. This function of x is geometric. If it's geometric, it will have a sum. The sum is defined to be a, how much is our a?
1.
Over 1 minus r. What is our r?
X.
Aha, the common ratio is r, or in this case, x. Put it all together, folks. Do you understand that's a function of x? Do you understand that's geometric and will have a sum?
Mhm.
Do you understand that this sum is only valid when this thing converges? Do you get that?
Yeah.
And when does this thing converge?
Between -1 and 1.
Yeah. This is awesome. This is really cool. Because here's what this says. Do you guys, this is equal, right? And this is equal, right? Because a series is a sum, and this is the sum of any geometric series when x is between -1 and 1, because that's when this series converges. That's therefore when we can find the sum. What that means is that this series actually represents the function f of x equals 1 over 1 minus x. That's what it represents. But only on a certain interval. Only between what two numbers?
Negative 1 and 1.
You got it. I'm using interval notation here, -1 to 1. The interval -1 to 1. So if you want, what in the world are you freaking talking about, Leonard? Here's the deal. Give me a number between -1 and 1.
Half.
A half, like a half. So if you wanted to, you could plug a half in here, right? And find out what it is. If you wanted to, you could plug 1/2 in here, and here, and here, and here forever, and add it all up. It's going to equal exactly what you can get out right here.
Cool.
It's kind of weird, right? So we're using these series to represent functions, or rather, we're using functions to represent series. Same idea. Show of hands if you understand the idea. Power series represent functions. That's what they do, because they have x's in them, functions of x. They represent these functions only on certain intervals for which the series converge. If you get that idea, you do understand power series. Do you understand power series? No, my speech is all off. Power
I thought you
series.
said parachute.
Parachute. Do you understand parachutes? Jump out of planes.
That's what I
If they
heard.
open, you live. That's how it works. Usually. Okay. Show of hands if you honestly do feel okay with that one. Are there any other questions whatsoever on that? So, our x is our input. Our sum is our output. That's how it works. Couple other little notes for you before we get on to it. I do want to kind of go quickly through this because I want to do an example to give you the idea of what you're going to be doing here. Question?
That's just a proof, right, of what you just showed us? Or am I mistaken? Did we find out if that thing actually converges at averages or not?
Well, that's the whole point, is that your x is a variable, correct?
Yeah.
So I can't tell you this converges all the time unless it converges for all x's. What you're doing is you're saying, okay, if this is this, and this is a geometric series, then I know when it will converge. What you're basically doing is giving me the interval for which this will converge. That's what you're doing, not the other way around. You're telling me that it will converge or won't converge. It will, at some point. Give me the interval that it does converge at. Does that make sense? Then, the interval that it does converge at is the domain of your function. Otherwise, there would be no sum. You could not define your function that way. Do you guys get the idea? You're saying, will this converge? Let's find out. If it does, what's the interval that it will converge at? What x's can I plug in? That's my domain. Because you're defining your domain to be the values where your series converges. Therefore, you get an output for your function. If you don't get an output for your function, how can you define a function? Well, I talked a lot. Did that make sense to you?
Yeah.
I think I said the same thing earlier, but I want to make sure you really got it. Now, let's talk about for general power series. So when we have a function equal to a general power series, where it doesn't necessarily center at 0. By the way, where's this thing centered?
C.
Do you understand that if I plug in C, all I get is a sub 0? Does that make sense to you? If I plug in C, everything else besides the first term is gone, because you have x minus C. If x is C, then x minus C would be 0, 0, 0, 0, 0, 0, 0. All I'd have is a sub 0 first. That's defined as your center. Okay, so the reason why we say it's centered at the origin, please listen carefully, is if I plug in like to, let's see, well, if I plug in my center itself, what I end up getting is something right around the origin. All right, if I plug in the center here, I'm going to get a sub 0. It's going to be centered at C, comma a sub 0. That's going to be the first point of my function. Now, what else do I want to say? Oh yeah, the domain, this is kind of important for you too. The domain of your power series is always going to be some interval that is centered around C. Notice something. What's the center here? The center, it's got to be a
The
constant.
origin.
The center is 0, the origin, 0. Look at your domain. What's right in the middle of your domain?
0.
It's centered at 0. That's where we get the word center from. That's what center means, okay? It's right at the center of your interval. So, note for you, the domain of f of x, the domain of your function, your power series, will always be an interval with x equals c at the center of it. Hence why we call C the center. Now, we have a few conditions for convergence of a power series I want to tell you about before we get to our example. I really hope we get to our example today. I'm not sure if we will, but at least we'll get through this. So convergence of a power series could be one of three things. First thing, you might have a power series where the function is only defined at the center. It could be defined just at x equals c. If it's defined at x equals c only, we would say that the radius of convergence is 0. A radius has this idea of you going around something, doesn't it? The radius of convergence is 0. It's only at one point. Let me make sure you understand this here real quick. Look at the board. This has a center of 0. It converges at 0. It has a radius of convergence of 1. Because it goes to -1 and 1. That's where it's... It kind of, yeah, sort of. It's not going really up or down, but it's centered at 0. It has a radius of 1. So we go -1 and 1. Does that make sense to you?
Yeah.
So we can have power series functions which are defined just at the center, and you have no radius of convergence. Therefore, your R, I'm going to define R in just a bit. R would be 0, and the interval would be this. It's a silly interval, but it'd be 0 is less than or equal to x minus c, which is less than or equal to 0. It would be, the interval of convergence would just be right at the center. Does that make sense? You sure? Okay. Number B. You could have an interval of convergence that incorporates or includes all x's. So are there times when a power series is always convergent? Yes. For any x? Yes. If I had a power series which converges for any x, for anything, what's the interval of, what's the radius of convergence, I would say? The infinity. It says, hey, you know what? I converge for any number, therefore the radius goes positive infinity, negative infinity, and therefore we would get an interval of convergence from negative infinity to infinity, centered at c, wherever that is. You guys okay with that one?
Yeah.
This one's not all that interesting. It just converges all the time. Okay, this one's not all that interesting because it has no radius of convergence. It converges at the center. Cool. C's where I like to, these are the more interesting ones to me. I like to spend most of my time here. We can have convergence for values that are within a certain radius. Where, and this is mathematically how you say this, where if you're outside of that radius, you get divergence. So let me make a couple notes on this one because I haven't defined this yet. First thing, that R is called your radius of convergence. What it means is how far can you go above and below your center? Remember, the center is always the center of your interval of convergence, okay? It's always the center. So this is how far can you go above and below that center of convergence in order to still have a power series that works for you. It still has a defined power series. That's what the radius of convergence is, above and below. Now, we can do this with this. Since the absolute value of x minus c is less than r, what that means is that negative r is less than x minus c, which is less than r, which means that if I solve for c, what we get is c minus r and c plus r. That right there is your interval of convergence. That tells you how far down and how far up you can go. Keep in mind, whatever these two numbers are, C will be in the middle of those because you're adding C to both sides. C is going to be in the middle of these, right here. C is going to be right in the middle. So C is going to be in the middle of this, whatever your constant is. You can also write it this way. C minus R to C plus R. Now, last little comment before I give you an example on this one. I want to get through at least one. Do you notice anything about this? I said less than, and I said greater than. Where's the equal to go?
The greater?
The equal to would be the endpoints of your interval. Did you get that? Now, I'm not saying anything about the endpoints. The endpoints must be checked individually. So the way we go through these is we find first the interval of convergence. We find this. Of course, we find the radius of convergence before that. That's going to lead us to our interval of convergence. After that, you must check whether each endpoint is included or not. Does that make sense? And to do that, we use convergence tests because we've already done that. So we plug in a value for x. Look at this. Listen, I'm trying to give you everything without an example, I know, but if you had this one and said, okay, we have a power series, now plug in a value of x. What that value of x does is it gives you a legit series, doesn't it? Not a power series anymore, but an actual series, which we can check with a convergence test. So to discover whether endpoints are included, you use a convergence test. You might want to write that down. So for endpoints, use a convergence test. For endpoints, use a convergence test. Would you like to see an example? I'd like to give you one before we head out, just so this is not all abstract for you. Yes, no? That clock's fast, remember.
Go for the gold, Mr. Leonard.
Go for the gold.
That's what the relay for life is.
Okay, so here we go. You find convergence first. This is going to give you the interval of convergence, or divergence, or, for the interval of convergence. And then you use your endpoints and use whatever you can to find out whether those endpoints are included with a different convergence test. Let me give you this one. So, firstly, what type of series?
Power.
Power series, of course. What's in there that would probably help us on what to do first? What do you see up there? Factorial tells you to do something up here. Now listen, what we're going to do is we're going to do the same test that we've just done in our last section, because we still need to find out the interval of convergence. We need to find out when this thing converges. So, what are we going to do with this problem?
Ratio.
We're going to do the ratio test. Now, keep in mind, when we do the ratio test says convergence, absolute convergence actually, when the limit of a ratio is less than what number? It shows divergence when it's greater than 1. It's inconclusive when it equals to 1. Does that make sense to you?
Yeah.
We're going to use that here. So I'll be upright and straightforward with you. You're going to be doing the ratio test an awful lot for this stuff. And the reason why is because the ratio test has a number associated with it. It says that it converges when something happens. Does that make sense? That when something happens, that's going to give you your interval that you want. So let's go as far as we can in the next couple minutes and see if we can do it. So because we get that factorial, we're going to do the ratio test. Listen, I'm going to go quickly through the ratio test because I want to get to the punchline of this problem. So, ratio test. Ratio test would do this. Ratio test would put, which one? A sub
A sub n plus 1.
over,
A sub n.
so we'd have n plus 1
Factorial x to the n plus
uh-huh, over what?
Same thing started.
1. n factorial x to the n.
Very good. That's exactly right. So, let's do it. Can you simplify this stuff? Firstly, tell me something about the absolute value. Do you need it or do you not need it?
No.
Better watch yourself there. What's x?
Oh,
Oh, we don't know.
Ah, is it always positive?
We
we
don't
don't
know.
know.
Then you better keep it. You better not just arbitrarily get rid of this thing. Does that make sense? So be careful. Don't just don't create your own map. Don't jump to conclusions here. That would be bad. Now, can we simplify this?
Yeah.
What simplifies? Lots factor. Yeah, lots. We can do the x. Where's the x going to be? X will be here. This is x to the n times x. X is on the numerator. This, do you remember, we've done this several times, you're going to get it several times more. If this is n factorial, this is n factorial times n plus 1. So when I simplify that, I get it n plus 1. So what we get is a limit, n approaches infinity, n plus 1 in parentheses times x. Are you okay with that one?
Yeah.
Strip off everything besides your x's outside of the absolute value. Here's why you can do it. Is n plus 1 always positive?
Yes.
Yeah, that's what we're going to do. That's what you guys probably meant when you said absolute value. You're thinking of just the n's. So when we go, okay, well, that's always positive, I can do n plus 1 outside of my absolute value. And now we're going to talk about this for a second. We're going to talk about when this will converge and when this will diverge. So, real fast, I'm going to write this twice. You know, actually, would you remember if I gave this to you tomorrow, where to start? Because I want to stop right now. I don't want to keep it any longer. So, we're working on our very first power series and trying to show when this thing is convergent. Now, the idea is use some sort of a test, typically it's going to be the ratio test, to find out where this series is convergent. You see, the idea was, and I'm not going to repeat the whole thing, but the idea is this power series represents some sort of function, but only where it converges. So we're going to find out where this converges, what our domain is. Basically, the domain is the interval of convergence, because therefore we can define our function as this series on some domain, where our x makes the series converge. That was all of practically our last time's lesson. You guys are all right with that so far?
Yeah.
So what we've done is said, hey, you know what? That's got factorials. Let's use a ratio test. So we're going to work this down. The reason why we like the ratio test is because it compares it to some number. It says this thing's going to converge when the limit is less than what number? Let's try this again. The ratio test says that this series will converge when the limit is less than what number?
1.
Now, here's the deal. Please listen carefully because this is where it's coming from. N's approaching infinity, right?
Yeah.
So, let me put in any number for x. What's infinity plus 1, by the way?
Infinity.
So this is going to be infinity. If I put in any number for x, take an absolute value of it, and multiply it by infinity, what's it going to be?
Infinity.
Unless that number is...
0.
I don't care if it's negative, because if I take absolute value of the negative, it's going to make it positive, right? So plug in negative a billion. Well, then you're going to get positive a billion. Hello, it's going to still be infinity. What's the one number that you can multiply by and get 0? Now, if you're thinking, well, wait a minute, isn't that an indeterminate form, infinity times 0? Not really, because this is x, it's not an n. It's not in terms of what this is. So this is legitimately 0, all the time 0, all the time 0. Does that make sense? It's different. So we have two situations. We have a situation where if x is any number besides 0, if x is any number besides 0, I take an absolute value of it, it's positive, it's some number. I multiply by infinity, and what I'm going to get is infinity if x is not 0. Does that make sense to you?
Yeah.
Are you sure?
Yes.
Okay. Now, if x is 0, I don't care what this is. How much is this going to be?
0.
If x does equal 0. Now here's where the type of test we use comes into play and why it's so important. Are you listening?
Yeah.
The ratio test says that we're going to get convergence or divergence based on what number we get. So when we get infinity, all you've got to do is compare these things to 1. So is infinity more than 1 or less than 1? Of course it's more than 1. So by the ratio test, because infinity is greater than 1, by ratio test, we get, what is it when it's greater than 1? We get divergence. Now, what about this one? When x does equal 0, we get our limit equals to 0. Well, how's that compare to 1? Greater than, less than?
Less than.
So by the ratio test, we get what?
Absolutely convergent.
That's right, absolutely convergent. I don't really care so much about the absolute part, but we do have convergence. You see, we said nothing about the function has to, the domain is where the x values make it absolutely convergent. It's just convergent. So where it does say absolute convergence, you're absolutely right, because ratio test gives us absolute convergence. We care more about the convergence itself. Does that make sense to you? So by the ratio test, this thing is absolutely convergent, therefore it must be convergent. Show of hands feel okay with that so far. Now, here's what this says to you. And we're going to do a few more examples to illustrate each type of case that you can have, okay? So here's what we've done. We said, how in the world are we going to find the domain for this? We already know a couple things. We already know a power series represents a function. What we don't know is where. The where is the domain. That's what you're trying to find. So you go, okay, what we find out with this is where this function is defined. So where a function, which represents this power series, is defined. Well, all right, well, cool. Use a ratio test, because the ratio test will tell you where. So we work this down. We got ratio test, no problem. Pretty easy. We got absolute value, but n's always positive, so absolute value is gone here. We got absolute value of x. This is not gone because x can be negative. X is any number. So, all right, well, there's two situations. We have if x does not equal 0, doesn't equal 0. That's a number. A number times infinity gives you infinity. Because infinity is greater than 1, we say, hey, you know what? By the ratio test, that's divergent. Here's what that means. If I plug in any number, listen carefully because this is a big deal, okay? If I plug in any number besides 0, do I have convergence or divergence? Therefore, our function is not defined for any number that is not 0. Does that make sense to you? So you go, all right, if I plug in x does not equal 0, a half, a third, negative 1, I don't care what it is, this thing is going to diverge. Now, the other thing says, okay, what if x does equal 0? If x does equal 0, then our limit equals 0. By the ratio test, that's less than 1. So by the ratio test, that is convergent. Therefore, our series convergence. And since our domain for our power series, the function of our power series, is all x's that make our series convergent, we only have one value that does that. What's the one value of x that makes this thing convergent? That's the idea. So this is one of those cases. Remember I gave you 3 cases of what you can have in your power series? I gave it to you last time. What I said was that your power series could be at the center only at 0. That's this case. There is no radius of convergence. The radius is 0. There's no space there. It says there's only one number you can plug in to make this series convergent, and the one number you plug in is 0. That's it. There's no radius of convergence. There's no interval of convergence. It just happens to be 0. You sure you're okay with that? And it happens to be at the center itself. So what we get out of this, we go, okay, cool. So by the ratio test, our domain is simply x equals 0. It says so right here. Also, little side note, the ratio, the radius of convergence is, what's the radius of convergence? 0. It's only one number. Radius of convergence is 0. Would you like another example that's a little bit different from this? This one has only one number that you're good at. It's only at 0. There's no other number that works. Therefore, our radius of convergence is 0. It's nothing. It doesn't go above 0 or below 0. It's exactly at 0. Show of hands if that made sense. Okay, let's continue. I want to do as many examples as I can to give you every type of scenario here. Okay, true or false? This thing is a power series. True or false? Absolutely. What tells you it's a power series? It's right there. Right there. That's a power series. Not a problem. Now, talking about our power series, does it represent a function? Or can we represent this as a function?
Yes.
This is a function in terms of x. For sure, it's a function in terms of x. Now, do we know the domain for such a function? No, but we're going to find it. That's the whole idea. So what we know is that this thing is a function of x. When I write it out, it's a function of x, but it's only a function of x where it converges. The where it converges is our domain. So we're going to find out where this thing converges. Well, let's try it. How do we do that?
A ratio test.
Let's do the ratio test. Ratio test is great for us for a number of reasons. Firstly, it gives convergence and it gives divergence, right? So it tells you where your series is convergent and where it's divergent. What that means is you can find your domain from that. That's why we use the ratio test so much. That's why I said it's so powerful. So let's set up the ratio test. I want you to set up the ratio test right now. See if you can do it. So you're going to write out what you're doing, okay? Write out ratio test. Don't forget your absolute values, because ratio test always has absolute values. Don't forget that one of these goes on top. A sub n plus 1 or a sub n. What goes on top?
A sub n plus 1.
Okay. I want to stop you right there. I want to make sure that you got this. Let's see. I'll have you do the rest of it kind of on your own, but I want to make sure you got at least this part right. Did you get -1 to the n plus 1 here?
Yeah.
Did you get x to the 2n plus 1 or the 2n plus 2?
Yeah.
You got n plus 1 in parentheses, or you did 2n plus 2, you distributed it, correct?
Yeah.
You didn't get 2n plus 1, did you?
No.
Okay, good. And you got the same thing here? 2 times n plus 1. Of course, we're going to distribute that, no problem. Probably could. And then factorial. How many people got that one? Now, the main denominator is pretty easy. It's just this thing again. that's quite a problem, isn't it? What's the next thing that you would do? What would you do if you had this problem with the test, which you're going to get something real similar to this? What would you do?
Cancel out the, like the negative ones because we talked about, you know?
Very good. Yeah, the absolute value is nice for a ratio test because the negative ones are gone. So this, gone. This, I don't care what it is, it's gone. It's gone. Because -1 to absolute, well, absolute value of -1, no matter what it is, or 1, it's going to give you 1 anyway. So these things, those are gone. So in terms of absolute value, that does not matter. What else would you do here, please?
From division.
Good. I'd multiply by the reciprocal, changing division multiplication. Very good. Let's do that step. If you haven't done it already, go ahead and do it now. Also, what I'm going to do at this point, you can do this too, I'm going to do my distribution. If you haven't done it already, this would be a good spot to do it. So here, I'm going to get my x to the 2n plus 2 over my 2n plus 2 factorial times 2n factorial over x to the 2n. True or false? I can drop my absolute value from here to here. True or false?
I say true.
True. True. You don't know what the x?
False, you don't know what the x
Squared,
is.
the x though. Oh, wait, it's squared. Never mind. It's squared.
They are. They're both squared. So you could actually do it. Does it matter?
No.
Not really. I'm going to put them just to get us in the habit, okay? So that we don't automatically drop them. I'm going to put them. But yeah, you could. If you see this, you could factor out that square. Do you see it? You could do it. You just fine. I'm going to put them just in case. So if you can make it that far, you feel okay with it. Now what would you do?
Simplify.
And simplify as much as you can. Now, when we simplify this thing, this is something you're going to have to be pretty good at. Being able to simplify x to the 2n, x to the 2n plus 2. You got to know what that plus 2 actually means here, okay? You got to be good at simplifying 2n factorial and 2n plus 2 factorial. You got to know what this means. So I'm going to go through it one time with you. From here on out, I'm probably just going to kind of simplify on my own because I'm going to expect that you understand this. Let's consider this first. This is the easier of the two. I'm going to write over here and then I'm going to erase it. So if you're going to write it down quickly. X to the 2n plus 2. If I can even write it down. Jeez. X to the 2n plus 2 over x to the 2n. If you know what this is x to the 2n times x squared over x to the 2n. When you multiply common bases, you add powers. Therefore, I can split up any addition of powers by multiplication common bases. That, therefore, gives you x squared. Feel okay with that one?
Mm-hmm.
So when I do this, I'm going to go, okay, well, boom, boom, x squared. So far, so good? Now, this one's a little more tricky to think of. It's not hard. It's a little more tricky to think of. 2n factorial over 2n plus 2 factorial. But think about what 2n plus 2 factorial would be. Do you understand that when you're doing factorials, you take the first term and then you multiply by the term right below it? So basically, you multiply by the number 1 less than it. So if I had 5 factorial, it's 5 times 5 minus 1 times 5 minus 2 times 5 minus 3. So this would be 2n plus 2. That would be the first term. Does that make sense?
Yeah.
Then I would have 2n plus, aha. Does that make sense?
Yes.
Then I would have 2n, and then I would have, oh, but wait a second. This is 2n factorial. All the rest of that stuff is 2n factorial. Show of hands if you understand that concept. We've used it before, but now we've never had a plus 2. So let me assure you, you can do this with a plus anything. It just is 2n plus 2 times 2n plus 1 times 2n times 2n minus 1 times 2. Oh, but that's this. That's exactly what this is. So basically, this gives you 1 over 2n plus 2 times what? Times what?
2n plus 1.
And that's it. Are you with me on that one? That one's kind of tricky for people. I want to make sure that you're okay with that.
Yeah.
Are you sure? So when you simplify something like this, you go, okay, what's here? Well, this is 2n factorial. This thing right here is 2n factorial with a little extra, with the 2 extra terms. The 2n plus 1 and the 2n plus 2. And that's it. For sure you okay with that one?
You
Okay,
just
so-
broke it up.
Say what now?
You just split it up.
You split it up. You go, well, what is this thing really? It's really 2n plus 2 times 2n plus 1 times 2n. Oh, but the rest of this is 2n factorial. So I can cross out all of this with this. And then I get 1 over 2n plus 2 times 2n plus 1. And that's what we're going to do here. Now I got to move back over here. So let's see what we have left over. Can you tell me? Because I'm going to get lost over there. So what do we got?
X squared.
X squared over,
2n plus 2.
uh-huh.
2n plus 1. Absolute value.
Okay, absolute value, sure. Do I need the absolute value anymore?
No.
For sure I don't. That's an x squared, there's no way it's going to be negative. This is both positive, there's no way that's going to be negative. So I can drop my absolute value right now if you want to. Now, here's the deal. Here's the deal. At this point, we're going to see what happens when we let our n go to infinity. We've already simplified everything we can, right? If we let our n go to infinity, what are we going to get?
Infinity over infinity.
Now, remember something about this. You're going to give me a number for x, right?
Yeah.
So pick any number, I don't care what it is, but it's a finite number. Does that make sense? It's anything. Take any number and square it. Do you understand it's still a finite number? Now divided by what this is going to. What's this whole thing going to?
Infinity.
Infinity. So what's this divided by this?
0.
For no matter what x is, right? Equals 0. Do you understand why it's for no matter what x is? Because x is not changing as n is changing. N is going to infinity. X is not. X is not based on n. X is this. X says pick a number, but it's one number. It's not going to be a variety of numbers. It is called a variable, understand that, but you pick one number. You say x is now, let's see, about 3/4. Okay. X is now 1 million. Okay. X is now -5. Okay. But no matter what it is, you're going to stick with that number. You got it? Then you square it, you stick with that number. Then you divide it by something that's growing to infinity. If you divide it by something that's growing to infinity, you have a finite number over infinity, and that idea is 0. And this works for all x. Here's my question. If this works for all x, what that says is that, are you with me?
Yes.
It says I don't care what you plug in for x, this series will converge. Does that make sense to you?
Yeah.
Now, how do I know that this thing's going to converge? How do I know that? What test did we use? And what answer did we get with our ratio test?
0.
And that is less than 1.
1.
Perfect. So we say this is less than 1, so therefore it converges by the ratio test. And what we've made our determination is that this is for all x. Now, if you have something that converges for all x, what that means is that I don't care what you plug into right here, this power series will converge for anything. We've just proved it. Does that make sense to you? It says no matter what you plug in, hey, guess what? It's going to be 0. Cool. Well, that means that we converge for all x. If we converge for all x, our radius of convergence says
Infinity.
infinity. So the radius r would be infinity. And our interval of convergence would be, well, this is hopefully pretty common sense. It says if you can plug in anything, right, your radius is infinite. If you can plug in anything, our domain is -infinity to infinity. Remember that the domain is all x's that make our series converge. If we can plug in anything to make our power series converge, then our domain's infinite. -infinity to infinity. Show of hands feel okay with that. Okay, we've covered 2 out of the three scenarios. We've covered one where we just converge at one number, just at the center, and that's it. The radius would be 0. We've covered the next one where we converge at any number. I don't care what it is. Our radius would be infinite, and we'd have -infinity to infinity. Let's talk about the third example. Question.
If you can plug in infinity into x,
But you can't.
okay, so it's everything except for actual infinity.
Well, x, you're
Finite
defining x to be any
It's a
number,
finite
right? But you
number.
can't say infinity for x, because that's not a number. We say plug in anything. Negative infinity to infinity, of course you can't get to here. That's why we use our parentheses. That's why in our interval notation you don't use a bracket. Because the idea of going to infinity is a limit, right? We've already kind of accomplished that. X does not get to go to infinity in this case. N is going to infinity in this case. Does that make sense? Okay, that's a good question. Any other questions before we do our next example?
And
We're going to do several more, but I want to make sure you're good with it.
And n is different, or infinity is different for n, because,
The idea of our limit here is saying that our n is growing, our terms are going to infinity. Our x doesn't change though.
right,
So once you start this, you pick an x, you stick with it. So it's first term, then first term times an x, then second term times an x, then to the second. Third term times x to the third, fourth term times x to the fifth. But that x doesn't change. The x is one number. So if we say, I don't care what number you pick, stick with it, the series is going to converge. That's what's going to happen here, no matter what x is. No matter what x is, that power series converges. Therefore, this represents our function for all x. Are you sure you're with me? You have to do one more?
Yeah.
So, the first example we had today, the one we just ended, that represented, a function represents that for only one value of x, that value of x would be 0. A function represents this power series for any value of x, all the time. It's going to converge for anything. Let's look at our third and final example, third and final scenario, I suppose. A seemingly harmless example. These are a little more fun though. These are the ones that I like. Okay, the first one, well, it's always going to equal. Well, the only time it equals 0 is if x is 0. Okay, this one equals 0 all the time. It's less than 1 all the time for any value of x. That's kind of boring. Let's look at this one. Let's look at what happens here. So, first thing, what type of series is that? Power series. That's right, it's a power series. So, okay, if it's a power series, well, we need to find out where this series is going to be convergent. In the first example, it was only at 0. In the second example, it was anywhere. In this example, we got to discover where this thing is convergent, because only where our series converges is where we can define a function for it. Only on the domain. So first example, domain was x equals 0. Second example, domain is infinity, negative infinity to infinity. Third example, we're going to discover where that is. It's going to take us a little bit of time on this one. So what would you do first?
root test.
You could maybe do the root test if you wanted to. I'm going to encourage you to stick with the ratio test. This is going to be a little hard to do the root test because you don't have a power of n there, so it'd be a little difficult. So I'd probably stick with the ratio test still. Ratio test works for powers of n as well. So try out the ratio test. Go ahead and set up the ratio test if you would. Question?
You don't want to use the limit test because we don't know what x is? Or could we?
No. The ratio test right there will give you where this converges and diverges, which is why it's so nice, right? Because it says, well, it tells you whether it converges or diverges, therefore it will give you the interval here of convergence and divergence. So we can't do really like the divergence test. You wouldn't use that here. You'd use a ratio test to tell you where it's going to be convergent and where it's going to be divergent, okay? Now, after we do that, I'll show you when you can use something like a divergence test. Okay, so we're going to use the ratio test, and I'm hoping you're already working on it. Ratio test says that, hey, do we need absolute value for a ratio
Yes.
test?
Yeah.
Yeah, because that n's changing, this is going to be possibly, if you give me a negative x, positive and negative, you need the absolute value. On the numerator, you need to have x to the n plus 1.
Over n plus 1.
That's right. And the denominator, you need to have x to the n over,
N.
that's it, and your absolute value. This one's going to be kind of nice. We have a limit We have n approaches infinity. Are we still going to have our absolute values?
Yes.
Absolutely, yeah, that's right. And we got x to the n plus 1 over n plus 1 times n
Was it X or X to the N? Squared.
over x to the n.
N.
Did I get that right?
Yes.
Okay. What would you do now? Simplify as much as you can. Also, collect your n terms and collect your x term. You'll simplify the x terms, okay? There's going to be only one x left. Collect your n terms. Pull those outside of your absolute value because they're always positive anyway. Does that make sense to you? So what I mean by this is, well, simplify what you can, but don't do stupid things. Don't go, oh, well, n and n. Cross out, I'm done. Don't do that. Don't do that. Simplify this, sure. X to the n plus 1 gives you 1 extra x. That's what the plus 1 is. It's an x to the first power. This you don't simplify right now. This you're going to do a limit with in just a minute. What I mean is collect this. Collect it and say, okay, well that means that we got a limit as n approaches infinity of n over n plus 1 times x in absolute value. Are you still okay with that?
Yeah.
You sure?
Yeah.
Now, is n over n plus 1 always positive?
Yes.
Yeah, because n's growing from 1 to infinity, yes it is. Is x always positive?
Yeah.
We can't make that jump. I don't know what x is.
Oh.
So what I can do, this is what I've been telling you, collect your n terms, pull your n terms out of your absolute value if they're all positive. They generally will be. So we're going to have n over n plus 1 times the absolute value of x. Now, this is why I like these. It's a lot more interesting. You got to do a little bit more work with it. Is it super hard? No, it's not super hard. But you get to do a little more work with it. So please pay attention. This is how you do the rest of the first two are kind of our basic ones, okay? X is 0, only for 0, no radius. X is infinity, radius is X is 0 for all x, therefore radius is infinity, no problem. This is more interesting. Take the limit as n approaches infinity of n over n plus 1. What do you get?
Infinity over.
How much do you get?
One.
Do L'Hopital. I don't care what you do. Divide by the largest power of n. Whatever. You're going to get 1. This whole thing is 1. Does that make sense to you? What is x as n approaches infinity? It's absolute value of x. It's whatever you have here. So what we end up getting, listen please, we get 1 times the absolute value of x. We get the absolute value of x. Okay, I need a show of hands if that made sense to you. Notice that the x doesn't change. It's the n that's going to infinity. Therefore, we have this idea of a limit of n like we normally have. We just have tacked on this absolute value of x. Now, here's the deal. This is why we use the ratio test. You see, the ratio test tells you when you're going to be convergent. This is the whole deal. So if you get this, you're going to get the whole thing, okay? The ratio test tells you when you're going to be convergent. When does the ratio test tell you that your power series is going to be convergent? When the limit is less than what? When what's less than 1? This, not x, the absolute value of x. So, did you guys catch that? We're using the ratio test, right?
Yeah.
Ratio test says, hey, go through all this crap, and at the very end, if this thing is less than 1, then you will have a convergent series, or you'll have a convergent power series in this case. The reason why this is here, why the less than 1 is here, is because we just use the ratio test. Show of hands if that made sense to you. That's why we're doing it, folks. Now, this is kind of cool. It's just very cool. Give me a specific value of x that you could plug in that you know that this series is going to converge for. Give me a specific value. 1/2 would be great. 0 would be fantastic. What else? -1/2. How about 2?
No.
No. That's bigger than 1. How about 1 itself? How about -1 itself?
No.
Yes?
I don't know. I don't know. The ratio test does not tell you.
Oh.
So here's what we know so far. Did you guys catch the whole idea about if you have a value between -1 and 1, between, not inclusive, but in between, you will for sure have a convergent power series. Then here's what we know already. Because of this case, because absolute value of x has to be less than 1 by the ratio test, we know that -1 is less than x, which is less than 1. We know x basically has to be between -1 and 1. Now let me tell you something. Right here is where you find your radius of convergence. It's really easy to do. Please listen carefully. What you do to find your radius of convergence is whatever is being raised to the nth power, x in this case, if it was x minus 1 to the n, you look for x minus 1. That's looking really nasty, I know, but if you had x minus 1 in there, you look for x minus 1 here, and then whatever that number is, that is what your radius of convergence is. So in our case, our radius of convergence is, what number is this?
1.
What's the radius of convergence?
1.
There you go. So you look for whatever's being raised to this power right here. When you get that, that is your radius of convergence. So the radius of convergence is 1. So far what we know is that, yeah, our power series represents a function, no problem. We've used our ratio test to say that this thing, this power series is going to converge when the absolute value of x is less than 1 for sure. So basically, when x is between -1 and 1, what that says is the radius. By the way, what's the center? What's the center of this? 0.
Origin.
0. The origin. Okay, 0. Hey, add 1 to 0, what do you get? Subtract 1 from 0, what do you get? That's why the center is 0 and the radius is 1, okay? And the way you do this is you find out the thing that's being raised to n, that's your radius. That's what it is. Now, the issue is, are the endpoints included or not? Well, the ratio test does not tell you that. You have to determine that. So now for our endpoints. It's not hard. In fact, it's all that stuff that you learn about series, which is kind of cool. So now for endpoints. Can you tell me, what are our 2 endpoints that we have here?
-1 and 1.
You gotta check both of them. There's only 2 things you gotta check. Two things you gotta check. There's only 2 endpoints. So we're gonna check -1, and we're gonna check 1. You go, wait a minute. How in the world can I check my endpoints? Well, let's plug it in. I just spit all over it. Did you see that? It's on tip of the gross. Plug it in here. So here we go. So if we have our series, n equals, did I say 1? Should have been 0. No, that one is 1. Interesting. So if we have our series going from 1 to infinity of x to the n over n. What am I plugging in for? Am I plugging in for the n or am I plugging in for the x?
X.
It says x. So what we get is a series from 1 to infinity of, oh, it can't be 0. We divide by 0. That'd be silly. Oh, I'm sorry. What's our x going to be? -1. Wait a minute, look at that. Okay, so if we plug in -1, what's it do? It changes our power series into just a typical series that you have seen before. This will change into something you've seen before. Tell me about that one. Alternating harmonic. We've done alternating harmonic before. It converges. So this is the alternating harmonic series. And because we've done this already before, we know this thing converges. If you, listen carefully, if you didn't know it converges, you would do one of the tests you've already done. You would do, you wouldn't do absolute convergence here, because if you do absolute convergence, you get 1 over n, and that would be divergent. But remember that when you're doing absolute, listen carefully to this one, okay? When you're doing absolute convergence, if you take the absolute value, and the series you get diverges, it doesn't mean the whole original series diverges. It means that it just doesn't absolutely converge. Remember that idea about conditionally convergent? It was the first thing that we talked about. Okay, so here you go. Well, let's do the alternating series test. The limit is 0. It's clearly decreasing. alternating series test says converges. So even if you didn't remember this, we get it converges. Now the next one, I'm going to move it up here, it didn't take a lot of work. The next one, if we get a series n equals 1 to infinity of x to the n over n, and we say, let's let our x equal 1, then we get the series from n equals 1 to infinity of 1 to the n over n. What's that?
Harmonic series.
1 to the n is always 1, isn't it?
Yeah.
What's that again?
Harmonic.
Tell me something about harmonic series.
Divergence. So we only include -1.
That, my friends, is how you find out whether or not your endpoints are included. So here's what you do for the most part on all these problems with your power series. It's not that hard. I know it looked originally like, oh my gosh, what are we doing here? It's not that hard. Honestly, what you're doing, you're taking your power series, you're going, okay, I know that represents a function. Where? Use a ratio test. The ratio test will tell you where. Remember, ratio test only converges for whatever you get here is less than 1. So ratio test gets cool, man. You know where that's going to converge. You just don't know the endpoints. Use those endpoints in your original power series with some of those tests you already know. Alternate harmonic, converges. Harmonic, diverges. What endpoint will we include? What endpoint will we not include?
-1 we include.
Good.
We
And
don't-
1?
We don't include 1.
Okay, so now the last thing we're going to do here. So last thing we're going to do, so our radius, what was our radius of convergence?
1.
And our interval of convergence is, what's our interval of convergence?
Bracket -1
Why is there a bracket there?
includes -1.
-1 makes that series converge. Remember, our domain is all the numbers that make our series converge. So if it converges, -1's included. If 1 diverges, 1 is not included. We already had the rest of it right here. So we go -1 to 1, it's just talking about the endpoints now. Does that make sense? By the way, what was the center for this?
0.
Where's the center between this?
0.
Does it make sense?
Yes.
Tell you what, let's go ahead and start with one more. This is practically, we have 2 more examples, and that's about it. Then I'll teach you how to do calculus of power series, how to do derivatives and integrals of this stuff. Yes, you can.
No.
Yes, you can.
You can do it.
Don't fret. Don't fuss. It's calculus.
Do it.
Doing so dorky. Can't help it. Oops. That can't be right. There we go. Oh dear. All right. Let's do it. Let's go through it right now. Firstly, what is this?
It's a
Power
power
You see something like that with X raised to the n, that's power series. Absolutely power series. For sure. Now, you tell me right now, where is this power series centered?
At 2.
Very good. Centered at 2. Which means this. When we get down to this part, our interval of convergence, the center is going to be at 2. It'll be 2. If it converges, it's going to be at 2. If it converges at more than one number, it'll be 2 plus and minus the radius of convergence. Whether that's infinity or whether that's a finite number. Does that make sense to you? But 2 will be at the center, for sure. Okie dokie? What are you going to do? Ratio test. Do a ratio test. That's not a power. Ratio test is going to give us something less than 1 anyway. Do a ratio test. What are you going to use for most of these things?
Ratio.
Do you understand that ratio test works when the root test works as well?
Yes.
Do the ratio test. So we're going to state what we're using, and then we use it. Be real careful on getting these correct here. Be real careful. Of course, the a sub n is pretty easy because it gives it to you, but don't make a mistake on the n plus 1 idea. Remember the a sub n always goes on our main denominator here, so we're going to have x minus 2 to the n over n squared times 3 to the n. You forget one little thing, and this problem explodes in your face. Okay? We're going to get that in a second. Okay, so up here we have, by the way, when you're doing the n plus 1, does the x ever change?
No.
So this guy is going to be there no matter what. X minus 2. The n does, though. We get n plus 1 over n plus 1 squared times 3 to the n plus 1. Oh, goodness. And I'm forgetting something. What else am I forgetting? Yeah, you're right. Is that important?
Yes.
In absolute value, forget your absolute value. Look at what happens. Look at. If you forget absolute value, you lose this, don't you? You lose your other side of your interval. That's a problem. Okay, so, oh my gosh, from here, is there anything that we can get rid of automatically right now?
No.
There's no negative ones, not like that alternating idea, so we'd have to go through and multiply by the reciprocal. And yes, absolutely, you got to simplify as much as you can. Do we drop the absolute values right now?
No.
Oh, no. The x is for sure. We can't drop that. So we got x minus 2 to the n plus 1. We got n plus 1 squared. We got 3 to the n plus 1. No problem. Now, multiply by the reciprocal. We got n squared times 3 to the n. We got x minus 2 to the n. And then we still have absolute value. I promise you, the simplification gets way easier when you get used to this. Right off the bat, you're like, oh my gosh, what are you doing? But when you get used to it, it gets really quick. It's really nice. You get used to what a plus 1 and a plus 2 mean as a power, and you can simplify stuff really fast. Have you already done it?
Yeah.
Probably. Tell me something that does simplify.
Yeah,
Yeah, that's the first thing I see too. So if I simplify 3 to the n with 3 to the n plus 1, I get
3.
and it's on the denominator, yeah?
Yes.
How about the n squared and the n plus 1 squared?
No.
No, you can't touch that. Do. Can't touch this. Okay, don't do that. I'm not wearing my hammer pants, but I should be.
You can cross out the x minus 2n on the bottom.
Sure. These are the same, except that this has an extra x minus 2. So if I do this and have the extra x minus 2, then what we end up getting, you know, we're not going to have much time after this anyway, so I'll erase this. What we end up getting is a limit n approaches infinity. Do I still have the absolute value?
Yes.
What's on my numerator, please? Over?
3n plus 1
squared.
minus
Or
3n squared plus 6n.
Just put
Oh,
your
wait.
steps.
Okay, x minus 2, no problem. N squared, no problem. 3, no problem. N plus 1 squared, no problem. Show of hands, feel okay with that. Here's what you do now. Please be careful. What you do now, you collect your n terms. You do not collect constants and x's. Those are important. So collect your n terms. What I mean is that this stuff, I'm going to move this off to the side. I'm going to get a limit. See if you can stick with me here. N over n plus 1 quantity squared. Do you see it?
Yep.
N over n plus 1 quantity squared. Notice how I don't have an absolute value. It's always going to be positive. Then I have an absolute value of x minus 2 over 3. Collect everything except for your x values and your constants. Does that make sense to you?
Yeah.
Honestly, are you guys okay with that?
Yeah.
How much is n over n plus 1? As n goes?
1.
And what's 1 squared?
1.
So this whole thing is 1.
Oh no.
So what is this whole limit equal?
2 over 3.
Absolute value of x minus 2.
Actually, I'm going to do this for you. Does this absolute value affect the 3 at all?
No.
That's what we get. Show of hands if you're okay with that so far. Now, here's the question. What test did we just use?
Ratio.
Yes.
When does the ratio test show convergence?
When
When the limit is less than...
1.
Again, this is by ratio test. That's why we're doing it, because ratio test says that our power series, any series, converges if the limit is less than 1. No problem. So this power series make the limit less than 1, therefore you guarantee this thing is going to be converted. Does that make sense? Definitely have that. Okay, now, what that tells us is that if I multiply by 3, what I end up getting is absolute value of x minus 2 is less than 3. You guys okay with that one? If you're wondering, why are you multiplying by 3 now? Here's what I'm trying to do. A lot of students get confused. Go, how in the world do I find my radius of convergence? Is my radius of convergence 1?
No.
Is it 3? Is it 5? Here's how you tell. See the thing that's being raised to the nth power over there?
Yeah.
The x minus 2? As soon as you isolate that, x minus 2 in absolute value, as soon as you isolate that, that is your radius. Does that make sense? So the radius is, perfect. Radius of convergence is 3. That's what this says right now. So I'm going to put this right here. We already know the radius of convergence is 3. Now, from here, all you got to do is find the interval of convergence, and it's so easy. It's really easy. All you got to do is solve for x. So if you solve for x, what an absolute value inequality means is you do -3 is less than x minus 2 is less than 3. That's what an absolute value inequality is, right there. Then if we add 2, we find our domain.
-3.
If you simply add 2. So you guys feel okay with that so far? So this is why you do your radius first, because right now it's kind of hard to see. It's not super difficult. You can still do it. By the way, what number is at the very center of this?
2.
2 plus 3?
5.
2 minus 3?
Yeah, 1.
Oh yeah. Radius is 3, center is 2. Now, what about the endpoints?
You test
Plug
it.
'em in, plug 'em in.
Can we do that real quick? Oh, what do I want to do? I'll do it here. You know what? I'm going to erase this. I'm going to do it over here. We're going to test for endpoints here. So last little bit, endpoints. So for our endpoints, we need, what's our first endpoint we check?
-1.
Don't be silly and check this. That's silly, okay? Make sure you solve for x to find your domain. This is the endpoints of your interval right here. So we do -1 and we do 5. So if I'm plugging in -1, what we end up getting, remember I'm plugging in -1 right here, we end up getting -3 to the n over n squared times 3 to the n. What that gives you, if you look at this real carefully, what this gives you is what?
1/n² times negative.
Kind of. It's kind of, almost. You're so close. You said one thing wrong, but almost. Do you notice how they both have the power?
Yeah.
So you can make -3
A -1.
over 3 to the n, right?
Geometric.
Times 1 over n squared. No, not geometric. Do you see that this is -3 over 3 to the n?
Yeah.
Times 1 over n squared. Okay, it's on denominator. How much is -3 over 3? -1 to the n times 1 over n squared. N equals 1 to infinity. Tell me something about this series. It's not a P series.
It's alternating.
Alternating series. You can do a few tests with this one. If you wanted to be really quick about it, do absolute convergence. Absolute convergence gives you 1 over n squared, yeah? P series, booyah, done. This series converges absolutely. If you don't need absolute convergence, which you don't, you just do alternating series test. So that's what I'll do because I don't need absolute convergence. I'll do by alternating series test. It's pretty clear that the limit is 0. It's very clear that this is decreasing. Limit 0, decreasing, alternating series, by alternating series test, convergent. Are you guys okay with that one?
Yes.
Could you have shown it a different way? Absolutely. You could use absolute convergence. Done absolute value, this is gone, 1 over n squared is a P series. Because the absolute value of our series converges, our series is absolutely convergent. Therefore it is convergent. Endpoint, no matter what, is included. Plug in 5. If we do that, we get n equals 1 to infinity of 3 to the n over n squared times, this one's even easier. How much is 3 to the n over 3 to the n?
1.
Pew, pew.
Wait,
5.
1 over n squared.
1 over n, tell me something about 1 over n squared.
That's a P
Oh,
series.
5 6 over 2, yeah.
See what now?
That P series.
That's P series.
Yeah.
Tell me about the P series.
P equals 2, greater than 1, minus.
Oh, you guys too fast. P series, P equals 2, that's greater than 1. Do you notice how what we're doing? Let's look at it. We're putting like everything we know together, right? I'm going to go through it one time here real fast to show you what we're doing. We're doing ratio tests to give us an interval that lets us know when our power series converges, when it represents a function. We're using all the stuff that we've learned already to do our endpoints. We're saying, hey, alternating series test, or absolute convergence, or a P series, or a geometric, or whatever you have to show that our endpoints are or are not included. So here's what we got. The radius of convergence is 3. The interval of convergence is -1 to 5. You
In
already
brackets.
have that. Now tell me about the endpoints.
They're included, so they're both brackets.
That's what we're talking about. Here's what it means. It means that this series represents a function of x that converges for -1 to 5. And that's it. Make sense?
Yeah. That's what, folks.
All right, so let's do it. The last example before we get on to the calculus of power series. From before, we know that right there, whenever we have an x raised to a power of n, we have this thing that creates a function of x. That's our power series. What we are focused on doing is how to find the interval of convergence, the radius of convergence, where this thing converges. Firstly, notice something about this power series. Where's the center?
1 or -1?
The center is
Oh,
at
0, sorry, 0.
0, that's right. Which means that whatever interval we get, it's going to be centered around 0, plus or minus some number. Whether that radius, that number, is 0, infinity, or an actual finite number, this interval of convergence is going to be centered right at 0. And you found 3 cases so far. You found those cases on your homework where it converges only when x equals 0 and diverges elsewhere. That's the most limited amount. Does that make sense? You found the cases where it converges at the center and some radius around it, where that radius is a finite number. And then we'd have to check endpoints, of course, whether it converges at endpoints or not. That uses the stuff we learned before. And then that's kind of the second case, the second least limited. And then the least limited is where it converges all the time for any x. And you hopefully, if you've done your homework or some of it, you've seen all 3 of those cases. Have you seen those cases yet? By the way, I do want to see where these things converge. They will converge somewhere. Okay, I want to see that. I want you, even if they go, it diverges when x doesn't equal 0, I want to see it converges when x does equal the center, wherever that happens to be. Does that make sense? Okay, so our last example says, all right, if that's a power series, let's go ahead, let's find out what the interval of convergence is, what the radius of convergence is, what's going on with this thing. How are we going to do that most of the time with this? Yeah, usually it's a ratio test, or maybe a root test. But you want some test that lets you determine the interval or the radius of convergence that says, hey, it's going to converge when this is less than some number, when this happens, because that gives us that interval. So let's go ahead, let's start. Do you guys want to try this one on your own? See if you can do it? Let's start with the ratio test. Write out the ratio test and see if you can do it. As you're working through this, can you tell me some of the key points about the ratio test that we need to know? Say what now?
It would take away the alternating.
It would. Why? What part of the ratio test takes away the -1? Okay, so ratio test has absolute value in it, no problem. What are some other key points about the ratio test that we need to know? Specifically, what goes on the main numerator? A sub n or a sub n plus 1? Okay, that's pretty good. Do you know anything about the convergence of the ratio test? When does the ratio test converge? Very good, when the limit's less than 1. And it diverges when the limit is greater than 1. Man, this is going to be a nasty one, isn't it? Let's see if you all got this. We got -1 to the n plus 1. We got 2 to the n plus 1. We got x to the n plus 1. We got square root of n plus 2. Do you see where that's all coming from?
Yeah.
All right, cool. We're just taking n plus 1 and putting it here and here and here and here. And then all over a sub n. So -1 to the n, not a problem. 2 to the n, x to the n. Square root of n plus 2. Show of hands if you made it at least that far. I'm sorry, n plus 1. Hopefully you didn't make it that far. I just like 2's today. N plus 1. Did you make it that far?
Yeah.
Fantastic. I'll let you know the ratio test. All right, so now what do we do? As much as you can. So simplification means get rid of your -1 to the n plus 1s or -1 to the n because absolute value gets rid of those things. It also means take your complex fraction and rewrite it. Do I get rid of my absolute value with a ratio test in a power series? Not generally, unless you have something like x squared where it doesn't matter, sure, but not generally, no. So we're going to have absolute value still. We'll have 2 to the n plus 1 times x to the n plus 1 all over square root of n plus 2 times the reciprocal of our main denominator. That would be the square root of n plus 1 over, well, the -1s, those are gone. Our absolute value does that for us. We get that. Did you get that far on your own?
Yeah.
Okay, now before you go any further, what are we going to do? Yeah, as much as you can. Simplify. And then after we simplify, we're going to strip off our n terms and leave our x terms. We're going to separate those things. So when we do this, I'm going to go through it quickly. I've always explained it a few times to you. When we simplify, you're going to have a lot of common bases raised to different powers. Just understand that a plus 1 simply means you're multiplying by 2. A plus 1 here means you're multiplying by an x. So what we're going to do, we're going to collect our n terms. If you notice this, there's a square root of n plus 1 over square root of n plus 2. I can make a big square root of n plus 1 over n plus 2. We're going to do that. So n plus 1, n plus 2 as the radicand of our square root. And then we got, what else is up there? 2x. Okay, if this is all an absolute value, tell me what do I do? What can I pull out of the absolute value right now because it'll never be negative? Good. How about the 2? Could I pull that out?
You don't know what x
Because
is.
x
Could I pull out the 2?
negative.
Yes.
I could pull out the 2. So if I wanted to, I could do a limit as n approaches infinity of the square root of n plus 1 over n plus 2 times 2 times the square root of x. I could do that.
The absolute value of x.
What did I say?
Square root.
Oh man, sorry. Too much painting. I told you, brain kind of. My bad. So square root of n plus 1. I just like square roots and 2s today. Don't worry about it. Square root of n plus 1 over n plus 2 times the absolute value of x. Oh my gosh! Tell me one more thing that we got here. What's going on? The limit. What's the square root of n plus 1 over n plus 2 as n approaches infinity inside of our limit? What's this do? Yeah, use all this stuff about limits that you know. N over, well, if you divide by the largest power of n, or you do L'Hopital's inside your square root, whatever you want to consider, this whole thing goes to 1. So what's our limit equal? Very good. Okay, let's put the whole thing together now. What test did we just use?
Ratio.
And when do we know that the ratio test converges? When the limit is less than 1. So if we just use a limit and say, hey, you know what? We use ratio test to find our limit, and we know that when the limit is less than 1, we know that this power series converges. Remember that a power series represents a function only when that power series converges. So that's the whole idea here behind using the ratio test is we want to find out when that actually converges so we know the domain of our function, the domain of our function for which our power series converges. Show of hands if you're okay with that idea. I know we explained this a couple times, I'll make sure you're with it. Do I stop here? No, but we're getting there. What we know is that 2 absolute value of x is less than 1 gives us our interval of convergence for our power series, for which our function will define that. That's our domain. Now, what we do here is we're always trying to find the absolute value of whatever is being raised to the nth power isolated all by itself on one side of our inequality. What that does, that will give you your radius of convergence. Have I told you that before?
Yes.
So what you're looking for here is, hey, if it's x to the n, I want x all by itself inside of an absolute value on one side of my inequality. So if I divide by 2 on both sides, that right there, as soon as you isolate that, you go, oh, cool, look at that. Hey, this is what's being raised to my nth power. It's isolated, it's inside my absolute value. Right now, you should be able to tell me the radius of convergence. What is it? Very good. So this right here says the radius of convergence is 1/2. Now, we keep going a little bit. We write out the definition of what an absolute value inequality is. Absolute value inequality says if you have the absolute value of x less than 1/2, that means that negative 1/2 is less than x is less than 1/2. And we're almost done. Are you guys okay with that one?
Yeah.
Almost done. What do we do next?
Check endpoints.
We gotta check those endpoints. Because right now, yeah, we have the radius, we know it's gonna be 1/2. We have the center. Notice how the center, 0, is right between negative 1/2 to 1/2. What we don't know is whether these two endpoints are included or not. That doesn't give us this with the ratio test. It doesn't give us it by just doing the simple mathematics. We gotta check the endpoints individually. Where do we check the endpoints? Say what?
The original function.
Original one. So plug him in. Let's see. If we plug in, where do we plug in the 1/2 and the negative 1/2?
X.
It seems that way, right? Because x is between those things. So if x becomes negative 1/2, we're going to find out whether that converges or diverges for that specific endpoint. Same thing with positive 1/2. Which one do you guys want to do first?
Negative.
Okay, negative 1/2. Does it matter?
No. We just like to go left to right.
So if we're going to check the endpoint negative 1/2, we're going to plug it in here and get a series n equals 0 to infinity of negative 1 to the n. We're going to have 2 to the n, and we're going to, what's the next thing?
Negative 1/2 to the end.
Yep, all over the square root of n plus 1. Now, because you did all that stuff in the previous sections, these ones should be pretty easy. These are going to be nice. Things that you recognize. You go, oh yeah, we could do this with it. We could do alternating series test, or absolute convergence, or we could do another ratio test if you really, really want to, or we could do a p-series, or a limit comparison test. All those things open up right now because we don't have any more x's. We have all constants. So simplify before you check them, but it's going to be something familiar. So here's how I would look at this one. Nth power, nth power, nth power. Do you see if I can make all those things to 1 nth power? Yes. Well, then we have negative 1 times 2 times negative 1/2. How much is negative 1 times 2 times negative 1/2?
1.
Positive 1. So this whole thing gives us a series from 0 to infinity of positive 1 to the n over the square root of n plus 1. Okay, well wait a minute. How much is 1 to the n?
1.
So no matter what, do you guys notice that when I have a negative times a negative, that gets rid of that idea of an alternating series? This is not alternating. It's just 1 to the n, or simply 1 all the time. So we don't need that n anymore. Now tell me something about this series. Can you work with it? Can you do something with it?
Comparison.
Okay, if we compared it, please listen carefully. I want to walk you through this because I don't want you wasting your time. You need to think about it, and I like that you're thinking about it. But if you compared it, this is less than 1 over square root of n, correct?
Yes.
And this is 1 over n to the 1/2, which is a divergent p-series. Are you clear on that?
Yes.
This thing diverges. This is less than that. Does it tell you anything?
No.
This is inconclusive. That does not help us at all. So even though we can compare it, we're comparing it to something that is bigger and divergent. That doesn't make sense. We want bigger and convergent. That would be great. But this is not that. Does that make sense?
Mhm.
Could you use a limit comparison test?
Yes.
That you could do. If you did a limit comparison test, then the series of 1 over the square root of n plus 1 compares to the series of 1 over square root of n. Sure, no problem. If you did the limit, since these both have positive terms, we'd have square root of n plus 1 over 1 over square root of n as n approaches infinity. This should kind of be old hat for you, right? You guys have seen this before, I know. And this would give you 1. When you work through it, that's going to give you 1. Quick head nod if you're okay with that one. Now, next question. If that gives you 1, this is a limit comparison test, is that inconclusive, or do you know something about this?
You know something.
You know something. With a limit comparison test, if the limit equals a number, I don't care what it is, if it just exists, if the limit exists, then both of these series have the same result. Tell me something about this series.
Divergent.
Tell me something about this series then.
Divergent.
So by the, very good, by the limit comparison test we said this, all right, this one acts just like that, think of the end behavior of your function. This one acts just like this one. If I compare them in a limit comparison test, compare them in a limit, and that limit exists, they both have the same result. If one diverges, the other diverges. If one converges, the other converges. So we base this, our given series, on a series we already know the result for. Whether it's convergent or divergent, doesn't matter. They're going to have the same result. So both series diverge by the limit comparison test. Since that was a p-series, with p equals 1/2. Oops. Okay, so let's put this into play here. Is the endpoint -1/2 going to be included in our domain of our power series? Okay, so since this thing diverges, we are not going to include -1/2. Can I show you something else, a different way to think about this? It's a little weird, but I want to open your minds to something a little bit different. You don't actually have to use a comparison test to do this. I'll show you this one. Check it. Sometimes you can manipulate your series in such a way to change it from what it is to what you want it to be. And here's how you would do that in this case. So notice something. If we start with n equals 0, what we're going to get is a square root of 0 plus 1. Do you get that? Well, you can manipulate these series as long as you start with the same thing and it follows the same pattern. For instance, instead of doing a series from n equals 0 to 1, sorry, 0 to infinity, if I start it at 1, then what changes about this is instead of having n plus 1 inside of my square root, all I need is something that takes this number and maps it to the same place that this did. So for instance, here's 1, here's 1, here's square root, here's n, here's plus 1. Okay, when I plug in my 0, I get 0, right? When I plug in my 1, I need to get 0.
1 minus 1.
N minus 1. Does that make sense to you? It's doing the same thing. Think about that. If I plug in 0 here, I get 1 over square root of 1. If I plug in 1 here, I get 1 over square root of 1. If I plug in 2 here, I get 1 over 3. If I plug in 2 here, I get 1 over 3. Sorry, what did I say? 2 here. 2. Yeah, right. So if I plug in the next one, it maps to the same fraction. Well, if that's true, then this becomes that. Tell me something about that one. So this becomes the same exact series. This is a divergent p-series. You can do it a different way. I just want to show you that one. Is it super important? Probably not. You can do a limit comparison test and get the same result. But I wanted you to open your mind just a little something else. Show of hands if that one made sense to you. Okay, cool. We're almost done. What's the last thing that we got to do here?
1/2 testing.
Yeah, let's do that one. Let's do the positive 1/2. So if we do 1/2, the series will look really similar. Except instead of negative 1/2, we get positive 1/2. What's going to happen with our numerator? Let's simplify that. What do we get? That's right. We don't have that negative we had here. So when I had negative times a negative gives us a positive, I don't have that here. So our series does look really, really similar. It's still going to be a 1, but it's a negative 1 to the n over the square root of n plus 1. Now this one, oh man, this should be ringing some bells. Tell me something about this series that you know right now. It's alternating. All right, so with alternating series, we take the limit. What's the limit of that series?
0.
Remember doing that? Limit as n approaches infinity is 0. If the sequence from which we get our alternating series goes to 0, that's like the divergence test for our alternating series. Next up, is our series, well, what's the next thing have to be? Is it decreasing term by term? Yeah, and that's really easy to show. So we'd say the limit of 1 over square root of n plus 1, that's our a sub n. So to get our a sub n, you cover up this, you go, okay, what's remaining after I take away the alternating part? That's our a sub n. If the limit as n approaches infinity gives you a 0, that's like passing the divergence test and saying, okay, it's not, maybe not divergent, you keep on going. After that, you say, is it decreasing? Is a sub n plus 1, which is 1 over square root of n plus 2, is that less than 1 over square root of n plus 1, which is our a sub n? If that's true, which it is here, this is definitely less than that for n greater than or equal to 1. This says it's decreasing. So by the alternating series test, we get convergence. Let's put the whole thing together then. Do you know what your interval of convergence is?
Oh, interval?
Your interval of convergence. Do we know what it is right now?
Yes.
Where does it start, ladies and gentlemen? Is the negative 1/2 included?
No.
Where does it end? Is the 1/2 included?
Yes.
So we know the radius is 1/2. We know the center is 0. We know our interval. We know everything about this. So for our last example, I want to make it real clear. Make sure you guys are really good at this. We got these things called power series, which are functions. Power series have an x in there. So when I write out the series, I get a function of x. Now that function is only defined where that series converges. That definition, that's our domain. So what can x be in order to make this thing convergent? That's why we go through all this mess. We go, okay, well, what's x got to be for that to work? What's x got to be for our series to converge so that it defines a function of x? We get all the way down to here, we say, okay, whenever I have my whatever's being raised to the nth power isolated inside my absolute value, this right here is your radius. If this had been an x minus 3, I would want an x minus 3 here before I determine my radius. Does that make sense to you? After that, after we determine the radius, that's all fine and good. We get our interval, and then we check our endpoints. The endpoints are going to be done with something you've done before in this class. Either an alternating series test, or a limit comparison test, or another test that we have, integral testing. I don't care what you use, as long as you can test this thing out. If you get, for an endpoint, that a series diverges, that endpoint's not included in your domain that makes this power series convergent, so defines our power series. If you get that the series, when you plug in that endpoint for x, does converge, then the endpoint is included. And this is what we're looking for. The radius, the center, and our interval of convergence that makes this power series work, makes it converge. Therefore, we can define a function by using that domain. Have I explained everything well enough for you guys to understand it? Are you sure? I don't want to leave anything hanging. Do you guys get the idea? Can you do it yourselves? Okay. Then the last thing we talk about in this section is how to actually do calculus with these power series, which is weird. Like, what? Calculus, what do you mean? How do we do derivatives and how do we do integrals of power series? And honestly, it's not that hard, but it leads us to something very, very interesting. It's kind of like our stepping stone between this section and the next section, which is Taylor polynomials and Maclaurin polynomials. Well, Taylor series and Maclaurin series. That leads to Taylor polynomials. But firstly, we got to learn how to do derivatives and integrals of power series. Well, how in the world are we going to do that? Well, you know what? Let's start with something general. Let's just build on it. So let's assume that we have this power series. So f of x is a power series starting at 0 going to infinity. a sub n x minus c to the n. Let's talk about the terms of what the series is going to look like. So we're going to say here that we have some power series. It will converge for some domain of x, therefore we're going to have this function. So where our power series converges, that's our domain for our function. Okie dokie. Now, what do the terms look like? What's the first term?
A sub 0.
Yeah, a sub what?
A sub 0.
A sub 0. How about x minus c? Is that going to be up there?
No.
No, because it's being raised to the 0 power. That gives us 1, so we can just get a sub 0. Plus, what's the next term going to look like?
A sub
A sub
1.
1, very good.
X minus c.
To the
First power.
plus what?
A sub 2.
Uh-huh.
X minus c to the second power.
Good, now we're getting the pattern. A sub 3, x minus c to the third, and it doesn't end. Well, here's the cool thing. You know about derivatives, right? Derivatives say, okay, well, take your function, and when you do a derivative, we basically just derive it term by term, don't we? And when we have pluses or minuses, we know that with derivatives, we can separate those pluses or minuses and just do the derivative of that term, put it back together with the sign, you're good to go. Well, if you think about it, when I do all my terms, tell me what a sub 0, and a sub 1, and a sub 2, and a sub 3, and a sub 4, and all my a sub n's are in reality. Are they variables or are they constants? So no matter what, that's going to be a constant. That's going to be a constant, that's going to be a constant, that's going to be a constant, and so forth and so on. The only place that I have things to derive, because I have a function of x, if I'm trying to find f prime of x, the variable is x here. The only place I have my variable is here, and here, and here, and so forth and so on. Does that make sense to you? So we notice that when we take derivatives here, am I going to need a product rule here?
No.
That's like a coefficient. Okay, it's like 3 or 7. I don't care what it is. It's a coefficient. So what we do with this is, yeah, if we have just a constant by itself, what's the derivative of a constant?
0.
Okay, so we're going to take a derivative term by term. The derivative of a sub 0 is gone. I don't care what it is. It's a constant. When you do a derivative of that, it's gone. So f prime of x gives us, firstly, 0. I'm going to write the 0 just so we see what's going on with that, okay? So derivative of a constant, man, 0. What's the derivative of this guy? What's that going to be? Not 1, no. If this was 3x minus c, it wouldn't be 0. It would be 3 times 1, x minus c to the 0 power, times the derivative of the inside, which is 1. And this is 1, this is? Please don't forget your basic calculus, okay? It's just the chain rule, folks. It's you bring down the power, you multiply by the inside, good to go. So this would be, in this case, what? Don't say 3, it was just an example. A sub 1, that's right, a sub 1. What? Okay, plus.
A sub
2.
A sub 2.
What are you going to do with this? If that's a coefficient like 3, you're going to bring down the 2, aren't you?
Yeah.
You're going to have
2A.
2 times a sub 2. You're going to have your inside, x minus c. You're going to raise it to 1 power less than what you had, to the first power, and you're going to multiply by the derivative of, which is 1 all the time. It's centered at c, it's just going to be x minus c. It's 1 all the time, so that's great. So we're using the chain rule, yeah, but what we're really doing is saying, okay, well, derivative of a constant is 0. That's a coefficient. I know that some of you go, well, wait a minute, a constant, derivative of a constant is 0. Well, yeah, it is if it's by itself with no variable. If not, then you're using, kind of technically using the product rule all the time. It's just the derivative of a constant gives you 0, so you omit half of it, and you're using the chain rule. You're bringing down your power. You're multiplying. You're taking 1 away from that and using the chain rule, multiplying by the derivative inside. The derivative inside is always 1 here. You with me?
Yep.
So tell me what the next one's going to be.
3A sub 3, x minus c squared.
and so on, and so on, and so on, and so on, forever and ever and ever. But look at what this is so cool the way this actually works. Check out what happens. So f prime of x really just does this. First thing, tell me where our series actually starts now. You see, our series here started at 0, we had a sub 0. Where's our derivative start?
A sub 1.
A sub 1 doesn't start at a sub 0 anymore, it starts at a sub 1. Why? Well, because the derivative of our very first term, gentlemen, gets rid of that constant. So this thing is gone, we start at a sub 1. Question?
Well, the a sub 1, because you said you're bringing the variable down and leave the inside alone, so where's the x minus c attached to the a sub 1?
Right here?
On that one, yeah. Why is that one going
The
right?
derivative of that is what?
What's 1 minus 1?
0.
Never mind.
Okay.
You're right.
It happens. I know I'm
It's
right.
my favorite.
You're right.
I like hearing that though still. Especially from my wife, that never happens. But joke.
Especially if she's Latina, so.
Anyway, so here's what goes on. When you take the derivative of a power series, your first term is a constant, it goes away. So we don't have the 0th term anymore. We start at the a sub 1 term, or when n equals 1. And are you with me? Now what's happened here is for every single term that we've had, we've taken the power, we've moved it down. But notice, 1, 1, 2, 2, 3, 3, n, n. We're moving the nth power forward. We're leaving the a sub n alone, actually. A sub 1, okay. A sub 2, A sub 3, A sub 1, A sub 2, A sub 3, no problem. And we're doing x minus c to, what's going on to our power? What are we doing with it? Okay. Do you see that this from here to here, look at that. It should look very familiar to you. From here to here, do you see that that is just the chain? Oh, that's all that is. It's just, or the general power rule, if you learned it as general power rule, it says, hey, take your power, move it down front, no problem, we got that. That's a coefficient, leave it. That inside of something, chain rule, leave it. Subtract 1 from your exponent, no problem. Multiply by derivative of the inside, hey, it's 1. It's just the chain rule. That's all this is. It's just very cool that that still works for our power series. Maybe it's not that cool. Maybe it's obvious to you because a sub n is a constant anyway. But most people say, wow, that's kind of neat. But when you think about it, it should be apparent. It should be, well, if that's a constant times something x raised to a power. You can use the chain rule with it. You guys with me? Okay, next one. So we had, let's call this part A, derivatives, part B, integrals. If I do the integral of f of x dx, let's go right from here. If I integrate term by term, which I can do, because if I can derive term by term, I can integrate term by term, no big deal. We've done that for years now. If I integrate term by term, what's this going to end?
Yeah, x, a.
Is it going to be a 0?
No.
Integrals don't work like that. If I do like 1 minus or plus x dx, the integral of 1 becomes, okay, sure, so I'd get like x plus x squared over 2. So, okay. Now, here, when I do my integration, it's not just going to be a sub 0 x, it's going to be a sub 0 x minus c. But the same idea basically happens. It'd be like integrating with a substitution, kind of like that, where you'd have 1 plus x minus 3, say, squared, or not squared, you just do it like that. You'd use a substitution, wouldn't you? You'd make u equal to x minus 3. And you go, okay, well, no problem. Then when I do my integral, that would be u. And when I did my u back to my x's, I'd get x minus 3. Same things happen in here. Does that make sense to you? Okay, so we get a, okay, no problem. What's the next one then? Oh, come on.
A sub 1.
That's going to, yeah.
1/2.
Am I going to have an x minus c?
Yeah.
What powers are going to be raised to?
Square.
over.
2.
Next one.
X minus C is over 3.
And so on and so forth, which looks like this. The integral of f of x dx, therefore, would simply be a series. This one does start at 0 still. We get a sub n, we get x minus c to the, let's look at what happened into our power. What's happening every single time? We didn't even have an x
N
minus
plus
c,
1.
now we have one to the first. We had an x minus c, but now it's to the second.
N plus 1.
That's right.
Over
Over what?
1 N plus 1.
That's right. Does that look familiar too? That's our basic integration rule. It just says, hey, you know what happens here? You take this, you add 1 to your exponent, bam. You divide by your new exponent, got it. We don't need to worry about the x minus c because when you do a substitution, it's like the most trivial of substitutions. The derivative of x minus c is 1, therefore your dx is a straight substitution to the du, whatever you use for your substitution, and we got it. Show of hands feel okay with this so far. You shouldn't. There's one thing I'm missing.
Plus C.
Ah. Aha. Don't forget the plus c, you see? You see? Now, there is one other thing that can happen. You see, all of these series start out with an interval of convergence, right? Some domain. So it's like from, like we had before, -1/2 to 1/2, where sometimes the endpoints are included and sometimes they're not included. Now, what can happen is, if you do a derivative, or if you do an integral of your power series, you can lose endpoints, or you can gain endpoints. What's interesting is the interval of convergence will remain the same. The interval is the same, but you can lose endpoints on derivatives, and you can gain convergence of endpoints on integrals. Does that make sense to you? So it's kind of an interesting idea, but when you do a derivative or integral of your power series, all you need to know is that the interval is not going to change, but the endpoints might. So be careful on that one. Show of hands feel okay with the idea. Now, I'm going to show you one example on how to use this very quickly. What we're going to do, and this is going to be our stepping stone into the next section, I want to find a power series representation for this. For ln of 1 minus x on the interval -1 to 1. I want to find a power series representation for that thing. What we're going to do is we're going to use this idea to do that. So, here's the start. Are you ready for the start? I'm looking for some function that when I take a derivative or an integral of it, it gives me ln of 1 minus x. I'll say it again. I'm looking for some function that when I do a derivative or an integral, it gives me this thing right there. Does that make sense to you? Now, I'm going to cut to the chase because I'm running out of time and I want to make sure that you get this. Well, here's the deal. I know that if I start with 1 over 1 minus x and I do an integral of that thing, the integral is going to be pretty darn close to that. Do you see that? It's going to be negative, but it's going to be pretty darn close. Are you with me on this, folks? So the integral of this thing gives us negative ln of 1 minus x. Quick head nod if you're okay with that. Okay, now, the other reason why I'm choosing this one, why I'm not saying, well, tell me something that I can do a derivative for that. I'm also trying to make a series representation. What I know is that this thing right here, this is so cool, this is the sum of a what type of series? Do you see it? That's the sum of a geometric series. This is the sum of a geometric series.
Geometric power series.
Of a geometric series with, okay, you tell me, if this is a geometric series, what's my A?
1.
Very good, A is right here. What's my R?
X.
Therefore, this is a geometric series with n equals 1 to infinity of 1 what else? But do you remember how geometric series look?
Yeah.
Geometric series look a r to the n minus 1. So a times r to the n minus 1. That's it. That's my geometric series. Okay, well, that's cool. Or you could do it this way if you wanted to. We all assume this way. N equals 0 to infinity of a x to the n. Either way. In both of these cases, what do the terms of your series look like? What's the first term here?
Yeah, good.
Notice the first term here would also be 1. You with me? So I don't care how you do it, either way. This one's a little easier to see, okay? But either way, if you did that, you'd probably raise the 1. But if you did this, you'd still get 1. Plus, what's the next term? Come on, we gotta quickly on this one. X to the, sure. Plus, what else? Plus, what else? Plus, what else? And so forth and so on. Okay, I feel like I've lost some of you. I've left you in the dust a little bit because I'm getting some blank looks. I never like the blank looks, you know. You know, sometimes when I speak Spanish to my dog, he goes, "Arr?" That was a little bit, never mind. Anyway, yeah, this is a little Greek, I get it, it's a little weird. Find a power series representation for that thing. What we're trying to do is say, hey, you know what, I've got a function that represents, I have a power series that represents this function on that interval. We'll talk about why the interval is there right now, actually. First thing we do is say, hey, find me something that when I take an integral of it, it gives me this thing, or that thing with a positive or negative. I don't care, as long as it's this thing, because negatives I can deal with. Well, I know that if I integrate this, it is going to give me this. What I also know is that this thing is the sum of a geometric series with a equals 1 and with r equals x. Look up the geometric series. This is going to be apparent to you. Well, a geometric series is always one of these two forms. No problem. It's n equals 1 with n minus 1, or it's 0 with n, and it's r to that power. That's exactly what we have right here. Show if you feel okay with that. Now, those terms are 1 plus x squared plus x cubed plus x to the 4th plus blah, 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 blah. That's how geometric series look, okay? Now, can someone out there who's thinking critically explain to me why this interval is the way that it is? Why x must be between -1 and 1 for this?
Because of the 1 inside the ln. 1 minus x.
Kind of.
Because of absolute value of r is greater than 1.
Why? Why is the absolute value of r less than 1 or greater than 1 important for us?
Convergence or divergence.
What type of series do we have?
Geometric.
So if this is not -1 to 1, then my x, which is my r, would be outside of the interval of convergence. Does that make sense? Geometric series only converge from -1 to 1. Hey, it's a geometric series, so because it's a geometric, x is r. You know what? Different r. R in this case. Since r must be less than 1 for convergence of a geometric series, x must be less than 1 for the convergence of this geometric power series. I wanted to write that out because it's important. Make sure that you actually get that. Do you guys understand the concept here? The reason why this is defined only on -1 to 1 is because we are going to be using a power series to represent this. We have to use a geometric power series to represent this. Because geometric series only converge when this number is between -1 and 1, it must converge when this number is between x has to be between -1 and 1. That's the only way that this thing is going to converge. Therefore, it's the only way that we're going to get a function to represent this power. A power series represents this function. Power series only represent functions where the series converge. Therefore, we have to have an interval for which our power series is going to converge to represent this function. Does that make sense? Okay, almost there. Very, very close to almost there. Well, what we have right now is this. We got, this is the sum of a power series. This power series looks like this. Therefore, 1 over 1 minus x is equal to 1 plus x squared plus x to the third plus forever and ever and ever and ever. What I also know about equations, can you guys make the jump with me? What I also know about equations, I can integrate both sides. And since I know how to integrate a power series, I can integrate term by term. That's where we're making this jump. We're saying, hey, integrate that term by term. Well, check it out. What's the integral of 1 over 1 minus x? What's the integral of 1 over 1 minus x? It's really not. It's not ln. It's not this.
Negative.
It's not that. It's close, but it's not that. It's negative. Do you know why? You'd have a u sub 1 minus x du equals negative dx. That gives us that negative. Does that make sense? Now, I'm not going to do a plus c here. I am on the other side. I'm not doing a plus c because very similar to our differential equation section, if I did a plus c, I could just subtract it and get a different constant, okay? So I'm not going to worry about it. Here I'm going to get x plus x squared over 2 plus x to the third over 3 plus blah, 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 and then plus c at the very end. So close, almost done. Tell me what I could do with that negative. Say what now? If I divide by negative, all these signs are going to change. I'll get ln 1 minus x equals negative x minus x squared over 2 minus x to the third over 3 minus blah, 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 minus c. So close, almost done. We got to find out what c is equal to. So if we want to find out what c is equal to, it's pretty easy to do. Do you understand that every single one of these terms are going to have an x in it except for my c? Plug in x equals 0. If you do that, everything goes to 0 except for my c. So if I let x equals 0, I get ln of 1 equals negative c. ln of 1 equals negative c. How much is ln of 1?
0.
So then 0 equals c. Okay. So ln of 1 minus x equals negative x minus x squared over 2 minus x to the third over 3 minus blah, 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 but no plus c. If we factor out that negative, which we could have done from the very beginning, we could have had negative x plus x squared over 2 plus x to the third over 3 plus blah, 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 blah. All we got to do is find a series representation for that thing, and it will be done. And it's really easy to do. What this is, can you represent that thing as a series? Probably x. X is going to be up there somewhere, yeah. To what? Over? Yeah. Do you guys see it? 1, 1, 2, 2, 3, 3, 4, 4, n, n. Where's n start? It starts at 1. It goes to infinity. So here's what we know. We can represent this function, ln of 1 minus x, by this series on what interval? Why was negative 1 to 1 important? Because that's really a geometric series. That's where we got this from. Okay, we can't define it other than that. So what this says is that on negative 1 to 1, this thing's going to converge. And it will represent this function. So if you wanted to find out, hey, what's ln of 1 minus 1/2? You could actually plug in 1/2 here, 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 and do it for infinity. It's going to be exactly the same thing. It's going to represent that function exactly on this interval, as long as you go n to infinity. Does that make sense to you? This is kind of out there stuff, but what we just did is we took a function and we used a power series to represent that function on a given interval that, for which our series converges. Show of hands if this one made sense to you. Okay. Any questions or comments at all before we stop? All right.